Right. And also on screen. Just give me 1 second. Um, window. Yeah. Okay. So, welcome everyone. This is the first tutorial session of this course, Thermal Physics in NPTEL. So, my tutorial session will be every week Sunday. Its time is from 7 to 9, but sometimes it can be late. Like today it is from 7:15. So around that time you can say 7 to 9. It's basically the rough time. And so basically what we'll do in this tutorial sessions is that the topics that will be covered in the main course material during that particular week, like say this is week 1. So whatever topics you are being taught in the week 1 lectures corresponded to that, you will be given a assignment to be solved, right? And you have to submit that assignment because that will be graded for you. And so in this tutorial session we'll be solving similar tutorial problems, similar numerical problems and solutions, learn their solutions, so that the agenda is that will help you to actually learn how to solve these kind of problems, so that you can use them and apply them in solving the assignments that is given to you by yourself. And basically that's it. And sometimes even apart from that, I may give you some extra problems, like say mostly we'll be solving similar sort of similar assignment problems, like 10 problems are there, like in this case. But sometimes I may also give you some extra problems which will be of similar kind and will be based on that particular lecture content of the week. And we'll try to solve them and see how, what can be the different techniques, and what can be the also the physics behind the particular problem that is given to you. Okay. So all right. So, can any of you just answer this, that if my screen that I have shared with you, that is that visible to you and I am properly audible? So we can start this class today. Okay, so any one of you, can you answer? Hello? Yes. Is anyone there in the class, or you have just opened your Google Meet and that? Um, all right. So if nobody's answering, then I guess I'll just start the discussion and the tutorial. Okay, and also one thing, I'll be solving the problems one by one. First, I'll explain the problems to you. What is the problem? What is the different conditions that is given in the problem, and what is the particular thing that you need to solve in that problem? And after that, once I start describing you how, what should be the way to solve the problem, at any point if you have any doubt in understanding how the thing is being solved, you can write there, stop me, you can unmute yourself, and you can ask the question to me directly, and I'll try to resolve your doubt. Okay, so then let us begin with this. So basically, first let me go full screen mode. Yeah. So basically, this is the week 1 tutorial, as I was saying. And as much as I have seen from the week 1 lectures, is that mostly you have to you have covered the topics of kinetic theory of gases. Then I think equipartition of energy was there later, but kinetic theory of gases, and then based on that the Maxwell's velocity distribution law. Um then the definitions of average velocity, RMS velocity and what was that? Most probable velocity, and mostly these kind of things, and also the equipartition theorem of energy. Then you have probably the topic on specific heat of ideal gases, the ratio, degrees of freedom of gases. So all these kind of topics have been covered in this week mostly, and the problems are, we will see, mostly based on that. So these problems are sometimes similar to the kind of problems that has been given to you in your weekly assignment, and I think one or two problems can be exactly similar also, so that is an advantage to you, that will already be solved in this tutorial itself. So anyway, this, I hope this will be helpful for you to solve the assignment by yourself, the one that is given to you in the the course page. Okay, so as I was saying, so let us start with the problems and solve them one by one. Okay, so let me choose the pen. Yeah, so the problem number 1, let us see what is this. So it is saying that convert 1.6 mole of KMnO4 to grams. So for this, I think you better keep your calculators with you, because there can be mathematical calculations for which you will be needing them, and it is better that when I am solving them, you yourself also take a pen and paper or copy, whatever, and solve them along with me, so that it is better for your understanding, and the solving purpose will be how it should be, to learn side by side when I am solving them. Okay, so first one is convert 1.6 mole of KMnO4 to grams. So this one is a very easy problem. This is a very easy problem, because this is not exactly related to the topic thermal physics, but this is something that is so basic that you'll be needing it in most of the problems that will be given, the numerical problems that will be given in this context to you. So first let us see how it can be done. So first of all, KMnO4 is the element that we are given, and it is said that there is 1.6 mole of KMnO4. So first let us see KMnO4, how many elements are there. So there is K, potassium, there is Mn, manganese, and then there is oxygen, O. So basically we have to know each individual component's atomic weight first, because KMnO4 is consisted of all these three type of components, right? So first we have to know the atomic weight of each atom. Like say, if you say the potassium atom, its atomic weight will be, you can check it from internet, Google. So the potassium atom's atomic weight is 39.098 AMU. So AMU is basically atomic mass unit, or in short sometimes we can also call it U. Okay, so AMU or U, whatever. So this is the atomic weight of potassium. Similarly, for now these are standard terminology, so I will not go into the details of what is atomic mass unit or what is exactly atomic mass all the time, but still if you have any doubt understanding in any term, you can ask me. Otherwise I'll just suppose that you already know this, because this is kind of a thing that most of us we study in our up to 12th, even we study this in physics, chemistry, both. So I think this will not be much of a problem to you. So manganese atom's atomic weight is 54.938 U. So AMU I am writing it short as U. Then oxygen, you have oxygen atomic weight is almost 15.99 or 16 U. Okay, so first of all, if once these things are known, then you know that total KMnO4's atomic or say molar weight will be the summation of all these components, right? So what will be the KMnO4's thing? So better I go to a blank page and start all over solving, so that you can see it much more clearly. So just note down the atomic weight, I have just now written earlier. Also I will be writing down here also, so you don't need to worry. Now first of all, we have to know what is KMnO4. This is a compound, okay, which has three elements, or three kind of elements are potassium, manganese and oxygen. So the molar weight of KMnO4 is basically the summation of all the three components, atomic weights summation, right? Because this is the compound made of all those components. So there is one atom of potassium, K. K is only one, so it will be just direct K atomic weight is, we just had written it down earlier on the last page. So this is 39.098. Then plus we have one atom of manganese. So its atomic weight is, we have already written, 54.938. Then you have O4, that means you have 4 atoms of oxygen. So you have to multiply by 4. You have to multiply 4 with the atomic weight of a single oxygen atom. So you have to take a 4 multiplication with 15.99, that is a single atom, oxygen atom's atomic weight, and this total thing will give you the molar weight of the total compound KMnO4, right? So let us take our calculator and see what is this thing. So this is 39.098 plus 54.938 plus 4 into 15.99, right? So this will give us, you can check also yourself, but I am getting 157.996 U or AMU, whatever. Now you see that I am writing this as U or atomic mass unit. So this basically means that this compound KMnO4, this is this compound's molar weight, right? So molar weight means weight per mole. Weight per mole of the compound KMnO4 is this. So in the question we have been asked that what is the weight for 1.6 mole of KMnO4, right? So this is very easy, that if 1 mole's atom equivalent weight is this, so this means 1 mole of KMnO4 is equivalent to, now we can write it in proper mass units, right? Mass or weight units. So this is gram, this will be in gram. So whenever you write U or AMU, you know that if this is molar weight or this is atomic weight, that means that 1 mole of that particular system, in this case this is the compound KMnO4, so that 1 mole's equivalent weight or mass is 157.99, almost 158 gram. So this will always be in gram, so that, keep that in mind. And so then 1.6 moles weight will be just 1.6 times this thing, 157.996. So what this gives you is that 157.996 into 1.6. So this will be 252.79 or around 252.8 in gram. So this is the answer. So let us go back and check whether this option is given. Okay, so this option is given, so our answer is exactly matching with option number D. So first question, option number is D, right? Alright, so this was just the initial starting point of this tutorial. This is given just for your practice, so that you can have a hang of how atomic weight or molar weight of these kind of compounds, any kind of element you have been given, how to calculate that, because that you will be needing very much in the next set of problems. Okay, now let us move on to the actual problems related to the topic of thermal physics. So the second question is, assuming that hydrogen molecules have a root mean square speed of 1270 meter per second at 300 Kelvin, calculate what is the RMS velocity at 600 Kelvin. Now before we move on to the solution of this problem, we have to first see what are the clues that is given to you in the question, first of all that, and then what is the specific thing that you have been asked to solve out of that problem. Once we know those things, first thing we do is that we get a connection in our head that okay, this is the thing that we want to calculate, and these are the clues that have been given to us to calculate that. So there must be some kind of a relation or some kind of a connection between those two, so that you can use your known clues and you get to the thing that you have been asked to calculate in the problem. So that makes the problem solving much easier than it should be. So basically in this case we'll do the same. First of all, let us break this part by part and see what are the clues given. So first of all, the system that is given to you is hydrogen molecules. So you know that hydrogen means H, right? H is hydrogen atom, single H. But for a hydrogen molecule, you know that hydrogen molecule is a diatomic gas, okay? So a single molecule of hydrogen will consist of two hydrogen atoms. That means it will be H2. So it has two hydrogen atoms in a single molecule. So this depends on the chemical structure of the particular system that you have been given. Like say O2. O2 is also diatomic like hydrogen, because a single molecule of oxygen, O2, has two atoms of oxygen. Similar, nitrogen, N2, H2O2, all those are a single molecule has two atoms. But let's say sodium. Sodium has only a single atom in a single molecule. So sodium, it has Na. It does not need Na2 or Na3, whatever. So it is only a single molecule. So similarly, these kind of systems you have to first consider it, that what is the system given to you. So this is hydrogen molecule. That means you have to keep in mind this is H2 and not H, okay, because that will change the calculation of the problem if you do that mistake. And the second thing is that root mean square speed. Now this is this is basically the RMS speed, or RMS full form is root mean square speed. So you have probably learnt about this already from the course lectures. So I will just directly get into the expression of this RMS velocity of gas molecules. So this is a standard expression. Sometimes I'll write this as CRMS. C subscript RMS means I mean the root mean square velocity or root mean square speed. So this is a particular formula which I'll go into later on. First, let us see the other clues that is given. So first of all, your CRMS is given to you in the problem, which is mentioned as 1270 meter per second. So first let me write what are the known clues to you in the problem. So known clues are your system is hydrogen or H2 molecule. This is the system you have to work on. And then the RMS speed is given to you, which is 1270 meter per second. And the temperature at which that speed is mentioned is also given as 300 Kelvin. So this, you know, because the velocity or the speed of gas molecules always depend on temperature. So because of that, basically because gas molecules move in because of the thermal energy, right? So thermal energy has a lot of role to play in the motion of the gas molecule. So because of that, whenever you are mentioning a particular velocity of a gas molecule, that is mentioned in a particular temperature, of course. So at different temperature, that value can be different. So at 300 Kelvin, this is the value of the RMS velocity. And in the question, they have asked you to calculate at 600 Kelvin what will be the RMS velocity. So you have been given a different temperature. Let's say your T1 temperature is 300, and then you have been given a different T2 equal to 600 Kelvin, and you have been asked to calculate what is the RMS velocity of that hydrogen molecule at that 600 Kelvin. So let's say for our convenience we denote this RMS velocity as 300 Kelvin as C1, because that temperature is called T1, and then the RMS velocity at T2 or 600 Kelvin, that we identify as C2. So basically we have to get the solution of C2. So C2 is equal to question mark, means you have to calculate this, and these are your known clues, that T1 is equal to known, C1 is known, T2 is known, you have to calculate C2. Okay, so once these points are being clear, then let me once again go to this page down. So you have been given a particular temperature 300 Kelvin at which the RMS velocity is denoted as C1, or which value is given to you as 1270 meter per second. Then another temperature T2 is given to you as 600 Kelvin, and they are asking you what is the CRMS or RMS velocity of the gas molecule, hydrogen molecule in this case, at T2. We identify this as C2, and C2 is equal to unknown. So we have to solve this. And the molecule you have to look at for this is hydrogen molecule. So as I said that because they are asking this question, so there must be some kind of connection that will lead you from these known clues to the answer. So that connection is very simple. You have to directly use the RMS velocity formula of the gas molecules. So this is, I will be directly writing this down. So this is CRMS equal to root over of 3 kT by m. Okay. So this is another alternative expression also. CRMS can be root over 3 RT by capital M also. So what is the difference between these two? So these are basically equivalent formulas, only different expressions, because whenever you are writing this K and small m, so here K is the Boltzmann constant, okay. So this is the universal Boltzmann constant of which the value is standardly known. So whenever you are writing this, you mean that this is the RMS velocity of a single gas molecule that you have been working with, single molecule, okay. So this small m will be mass of a single molecule of that system of gas, mass of a single molecule. Okay, so although this kind of clarification is not that much needed for solving this problem, but I am beforehand telling you this so that because these are related things. So whenever we approach a problem similar to this where you need to use this idea later on, so this will be easier for you to directly take that point. And also I am saying that the equivalent expression of CRMS can be root over 3 RT by capital M, where instead of K you write R and instead of M you write capital M. So what is the difference? So this is for the RMS velocity for 1 mole of the gas. The earlier one was for one single molecule and this is for 1 mole of the gas. 1 mole means that has Avogadro number of molecules present in that. So this is basically a combination of many molecules, right? 1 second. I think there is someone. Okay. I think I had stopped sharing by mistake, so let us get into that again. Okay, so basically whoever has joined late, so basically we are just solving the similar tutorial problems that will be helping you solving the week 1 assignment. So we are not far ahead, we are just in question number 2, so you can just follow in from here. The idea is that you have been given hydrogen molecule as your system, which means H2, and you are asked that if the temperature 300 Kelvin, the RMS velocity of the gas is known and that value is given to you as 1270 meter per second, then what will be the, one sec, so yeah, so there can be sometimes I cannot maybe see your message, or okay, so I think you have answered the question or something. So anyway, if you are solving along with me, then that is better, but I'll be anyway solving this because for the others also. So just follow it, and if I make some mistake at some point, just let me know, okay. And it is kind of difficult for me to stop my sharing screen and go back to the main page in the Google Meet page time by time to see if there is a message or anything. So I think it's better if you have something to say or something to ask, you directly like switch on your mic, unmute yourself and directly interact with me, okay. That will be much better for all of us. Now, so this was the idea that you have to know the connection between the temperature and the RMS velocity of gas molecule so that you get the answer straight. And in this context, I was just telling you that if you have been asked for a single molecule, then CRMS will have a form like this. But you have been asked for 1 mole of the gas, then instead of K you write R, because R is the universal gas constant, which is nothing but K times Na, and Na is the Avogadro's number. 1 mole of gas will have Avogadro number of molecules, or 1 mole of gas equal to Na number of molecules. So you know the number of Na, this is standardly known as Avogadro number 6.023 into 10 to the power of 23. And because you have 1 mole, so this, instead of a single molecule mass, this is the molar mass you have to write. That means the mass of the system of 1 mole. So this is the basic idea. Now for our problem, we will not be needing the value of mass or these constants, because there is a direct proportionality relation, right? So because you have to write CRMS is proportional to root over of T, because other things are constant. Other things means if that is a Boltzmann constant, then it is constant. 3 is constant. Mass, because we are talking about a single similar system, like there is only a single system hydrogen molecule, so the mass will be same for that system, so that will also be a constant. So the only variable is temperature, and this is the relation with temperature and the RMS velocity. So then you just directly write it as a ratio. So because we have denoted C1 and C2 as the RMS velocities for T1 and T2, so by that we go like C1 by C2 equal to root over of T1 by T2. Okay, so if that is the case, then you just now put in the values that you know and then get the value that is unknown to you. So C1 was mentioned to you as 1270 meter per second. Someone has joined the chat, I think. Just let me admit. Okay. Okay, so let us continue. So the second problem we are solving. So this is the relation we are using. Now C1 value is known, C2 value is unknown, so we keep it as C2. Then T1 is known to you as 300 and T2 is given as 600. So this will be cancelling out and this will be half. Then you just get C2 is equal to 1270 into root over 2, which is, if you calculate, 1796 meter per second. So I think one of you answered the question right, that it will be option number C, that is the answer of this problem. So very well. So you have understood the problem, I think. So let us move on. The answer is question number C, right? Now question number 3. So again, let us read the problem first. It is said that calculate the fraction of oxygen molecule with velocities between 199 meter per second and 201 meter per second at 27 degrees centigrade. And these are the 4 options that is given to you. Now first, what are the clues given to you? So the clues are, your system is an oxygen molecule. So like hydrogen, it is also diatomic molecules. It has 2 oxygen atoms in a single molecule. 2 atoms in a single molecule of oxygen. And then velocities ranging between a C value of, let's say this is our C, okay, 199 meter per second, and the other value is not much different from that. It is just C plus DC, a small amount of deviation from this C value, which is 201 meter per second. So basically DC is the difference between these 201 meter per second and the other value 199 meter per second. So DC is basically your 201 minus 199 equal to 2 meter per second. Now, and the temperature is given as 27 degrees centigrade, means you have to always convert it, remember, always convert it into Kelvin, because in thermal physics, anything, in any standard cases, you would never convert units, use units like degree centigrade, Fahrenheit. These are only for our practical uses, but whenever you have to use this in a calculation or a standard method, you have to convert it into Kelvin. So remember that, don't make this mistake. So this will have to convert into, this will give us 300 Kelvin. Okay, and why I am writing this as C and C plus DC, I think by it you have a guess, like the problem is based on the Maxwell's velocity distribution law, because that only gives you how many number of molecules are present in a particular range of velocities, right? So basically, if you know that, you can also get the fraction of molecules as well. So I think this velocity distribution law has been, you have studied this already in the lectures. So I'll be directly writing down the formula and the basics basically. So the main clue is given, that you have to just understand that instantly, that this is the once you see that there is a velocity range that is very close enough given to you, and you have been asked about something about the fraction or the number of molecules, etc., and because it is a velocity distribution kind of a thing, you have to instantly relate it that you have to use the Maxwell's velocity distribution law to solve these kind of problems, because you will be seeing like many problems based on this particular formula. And so basically this is the easier guess to have whenever you have a problem like this. So Maxwell's velocity, if some of you has already solved this, or you are solving this, then then please go ahead. Later on when you solve by yourself, just check with my answer whether it is matching or not. Maxwell velocity distribution law. Okay, now it has a like pretty large form that is given in the formula. So basically in the formula, for the formula is basically that if you have a gas molecules, there are, if you have a gaseous system basically, so all the different molecules in that gas will be moving in different velocities, which is usual. Now how can you know that what is the typical distribution of that velocities in those different gas molecules? So because of that, this kind of a distribution formula is relevant. And basically it is some kind of a probability distribution sort of a thing you can relate with, that basically you have to see what is the probable number of molecules in a particular velocity range that is present in the gaseous system. So based on that, I'll just first write down the expression, and then I'll explain what term explains what. So the formula, main formula is that dn subscript c is equal to 4 pi capital N m by 2 pi kt to the power of 3 by 2 e to the power of minus m c squared by 2 kt. So this is k 2 kt c squared dc. Okay, so I know this is a pretty, lengthy kind of a expression, but it's better if you like have a hang of it, because in this chapter, especially in kinetic theory, this formula will be very relevant to you. So if once you this is a basically this comes from a huge derivation, right? So once you get the hang of the derivation, you do it yourself several times, then I think the main form will be actually visible to you, even if you can't remember explicit terms. But it's better if you remember totally, because most of the cases in the problems it is not mentioned, and if you need that, then you have to memorize it basically. So I prefer to memorize the formula, the specific terms as well, not blindly memorizing it, but obviously knowing the type of the structure of the card that will give and the derivation, etc. So what are the meaning of the different terms present here? So let me tell one by one. So this first one is dnc. This is nc subscript c, means this is the number of gas molecules having velocity in the range c to c plus dc. Okay, so now why we are talking about c and c plus dc? Basically we take a particular velocity c, and then about that velocity we add a deviation. Let's say we have average velocity, we have some velocity value of 5 meter per second. Now you also want to know what is the some molecule has velocity, this 5 meter per second, don't take the absolute value as true. I am just giving you an example. Let's say one thing has a velocity of 5 meter per second, and there is another thing which has a velocity of 5.5 meter per second, 5.2 meter per second, these kind of things. So whatever particles that has velocity around 5, in a very close enough regime around 5, then you can like for a probability distribution kind of a thing, you can couple them together, you can particularly categorize them in a particular category. so that for the ease of the calculation, otherwise it will be too much complex, right? You have to categorize it by some sense, but you cannot categorize probably 5 meter per second and 50 meter per second because they are too much different from each other. So there has to be some closed spaced interval. Closed spaced interval is necessary for getting this kind of a formula categorization. So here this closed interval around that you take around c is the small velocity interval or range, whatever you can say, from c. So that let's say if you have c is equal to 5 meter per second and you have another particle going in c equal to 5.5 meter per second, then that will also be considered in the same distribution, only the velocity 5.5 will be considered as c plus dc, where dc equal to 0.5, right? So same kind of thing will be like doing here also. Now this capital N, what is this capital N? Capital N is the total number of molecules present in the gas. Now this total number of molecules capital N can have any values c from 0 to infinity. It can have any value. So infinity is not absolute infinity. Obviously it has to be much less than the speed of light. But because most of the particles has the speed which is far lower than the speed of light, so we can approximately, for the sake of the ease of mathematical calculation, we can approximately take the upper limit as infinity. Okay. So this is the total number of molecules. Now small m, this is important. Small m is the mass of each molecule. Mass of each molecule. Remember, for each molecule, not molar mass. Okay, so it is the mass of each molecule. K is a Boltzmann's constant. T is the temperature in Kelvin, in which we are seeing the velocity distribution. And then this is an exponential term. This is basically a Gaussian term because it has e to the power of minus some x squared sort of thing. And again you have another dependence on c as c squared. And this is dc. Dc is basically the interval, as you said, as we just learned. So if this is the number of molecules that is present with the velocity between c to c plus dc, then what is the fraction of molecules that we can get very easily is that fraction means you will have dnc by n, right? Okay. Yeah, so you want to ask a question? If you have something like, because you have raised a hand, if it is by mistake then okay, but if you want to ask something you can ask me. Okay, so you are not asking. Okay. Yeah. Hi.
Ma'am, please use white color, ma'am. It is not visible, ma'am. You are
This is
using
not
black
visible.
screen and red color. It is not
My
visible,
screen is
ma'am.
not visible, you are saying?
Yes, ma'am. Screen is visible. When I write in red color, that
Okay,
is
okay,
not
red color.
visible.
Okay, okay, got it. Oh, I'm changing the color. I'm changing the color. So the blue one is visible, right?
White is best, ma'am.
White is best. Okay. That's fine. I'm just changing the color. Thanks for letting me know. I actually did not realize. Okay, so I guess this much part I have already also verbally mentioned to you. So probably I'll not be changing the color and writing this down again. But just you have the idea, right? So what term is what. So I'll just be using white in this case because that is much better visible to you. Okay, so as I was saying that dnc by n is basically your fraction of molecules. Fraction because dnc is the actual number of molecules in that interval and n is the total number. So the ratio is the fraction of molecules having velocities between c to c plus dc. So I'm just writing it in bracket. I'm not writing the full sentence, but you can understand, right? Now, okay, so this was the idea. Now, using this idea, you have to solve this question for oxygen molecule you have been given in the problem. So this is O2. This molecule has 2 oxygen atom. Okay, so you have to get the fraction, that means dnc by n for O2. So for that, what are the terms that will be needing to know? First of all, this 4 pi is a constant that does not matter. So this n comes below. So dnc by n it becomes So then dNc by n will be, so I'll be just erasing off this n from here because this is coming down in the ratio. And 4 pi is a constant, so it remains, its value is known. Now you need to know what is small m. That means each oxygen molecule's mass we have to know. Then K value, the Boltzmann constant is standardly known, universal constant. T is the temperature, which is mentioned in this case 27 degrees centigrade, which we had converted into Kelvin. So this is 300 Kelvin. This is also known. And again the similar terms are present in the exponential. Now C is basically the so you have two velocities mentioned. One is 199 meter per second, and the second velocity was C plus dc, because this is the like C is one end of the range and C plus dc is the other end of the range. So this is 201 meter per second they have mentioned. Then what is the interval length? So this is dc equal to just 201 minus 199, which is just 2 meter per second. This is the interval. Now by this you know also dc and you know also C. Okay, so now sometimes there is some like, okay, so now first let me just solve it as it is, then final answer, during the final answer I will just explain properly. So then for oxygen molecule, let us first, the mass, what should be the mass of the oxygen molecule? So mass of a single molecule, you know that the standardly known oxygen molecules mass is 32 atomic mass unit, right? 32 because there are two oxygen atoms, each is of 16 AMU, so there will be 2 times 16, which is 32. Now AMU is atomic mass unit, you have to convert it into gram. How should you do that? Is basically you have to multiply it with this term 1.66 into 10 to the power of minus 24, then it becomes gram. And then if you want to do everything in SI, then you can also convert it into kg, then it will be like 32 into 1.66 into 10 to the power minus 27 kg. So if you are wondering how I am like directly multiplying it by this point, so I think this is probably known to you, but the thing is that you have to just use this AMU units corresponding value, and do not use this directly as 32 gram. That will be a huge mistake because this is in atomic mass unit, not in gram unit. So for converting into gram, so this means that Avogadro number of molecules, this is a molar weight. So 1 mole is equivalent to Avogadro, N is the Avogadro number, Na number of molecules of the system, and the total weight of that much number of molecules is 32 gram. So what will be the single molecule's weight? So for one molecule's mass, it will be like 32 by Na in gram. So Na, this value is known, 6.023 into 10 to the power of 23, and in gram, so when you take it up, it will be simply 1.66 into 10 to the power of minus 24 gram. So I think this derivation, this thing was unnecessary probably, but I still mentioned it because a lot of times people do mistakes by just converting these units and the answer comes different. Okay, so this is in kg. This mass is also known to us. Now we'll directly just put down every component that we have known and we'll just directly get the ratio of dNc by n. So now do this part very carefully because there are a lot of terms. So dNc by n is a fraction is equal to, it is equal to 4 pi, then m by 2 pi kt was there, right? So m by 2 pi kt, let us write down the m value that we have just got. So we are doing everything in SI, so this is in kg, this is m in kg, by 2 pi into k is Boltzmann's constant, which is 1.38 into 10 to the power of minus 23 joule per Kelvin. That means this is the SI unit. Then temperature in Kelvin, T as 300 Kelvin. Then there was a power of 3 by 2. Okay, so up to this part we have done. And then e to the power of minus mc squared by 2 kt. So you have exponential of minus, again m 32.1.66 to 10 to the power of minus 27. C squared is basically, so here C is your 199 meter per second. So this is also in SI unit, so you don't need to convert anything. MC squared is basically 199 squared divided by 2 into kT, which is K is 1.38 10 to the power of minus 23 into T is 300 Kelvin. Then you have this C squared and DC, right? So C squared is basically again just 199 squared into DC is your 2 meter per second. So everything is in SI, we have just compiled together. And so basically you just take your calculator and calculate this carefully. So I have already calculated it, so that I'll be writing down the terms. It will be like 2 into 10 to the power of minus 3. This was a fraction, right? So this will have no units then. But you will see that in the question there is no option directly given as 2 into 10 to the power of minus, what was I? 2 into 10 to the power, okay, 1 second. Yeah, 2 into 10 to the power of minus 3 we got. But you see that there is no answer that is much closer to that. One answer is there, which is this 2.29 10 to the power of minus 3. This is the only closest possible answer to our case. But you can ask how to get the exact answer, or why we are not getting this answer that they have mentioned in the problem. The reason is because sometimes people write this C to C plus DC when they take that range. So in the formula, when you use the C value, instead of using this 199, the starting value which is C, they just use the average of these two ranges. Like in this case they have averaged this out. So they have just basically used 199 plus 201 by 2, which is 200 meter per second. So if you use in the formula, in the mathematical formula, if you put in the value of C instead of 199, if you use 200, you will see that you will get exactly this value, 2.29 10 to the power of minus 3. But I think I prefer to go with the usual standard method, because we have to, in the formula itself it is mentioned that C to C plus DC, so our starting value is C, which is in this case 199 and not 200. So anyway, often you can use the closest possible answer to the actual answer. So this is in this case 2.29 10 to the power of minus 3. Okay. Yeah, Anupam Kumar Malakar. Yeah, Anupam, so you want to ask some question?
And then what should we do? What should we use as DC?
I just told you that DC is basically the interval length between the two velocities. So in this case 201 minus 199, which is 2 meter per second, is your DC. It is basically the difference between the two velocities that you have been given. Basically it defines the range. 199 to 201, that means there is a 2 meter per second difference. That is your range or interval in this case. Okay.
Okay, ma'am.
Okay. So should we move on then? In the next question, then I'll start to solve. So okay, so this one is done. Now question number 4 is that estimate the temperature at which the root mean square of nitrogen molecule in Earth's atmosphere equals the escape velocity from Earth's gravitational field. So this question is interesting because this is not like the other standard questions. There is also this gravitation sort of thing involved, which makes the question interesting. But also this thermal physics idea will also come because there is this RMS velocity mentioned, right? Now it is saying that at a particular temperature, because always these velocities are defined, has to be defined at a particular temperature, and that temperature you have been asked to estimate. That temperature is unknown to you. You have to get that, and it is, as a clue, it is given to you is that the RMS velocity of nitrogen molecule. So in this case our molecule is nitrogen, which is N2, again a diatomic system. So when we calculate the atomic mass and the molecular mass, we have to be careful because there is two atoms sitting in a single molecule. And it is said that for that system, the RMS velocity of the molecule in Earth's atmosphere is equals to the escape velocity from Earth's gravitational field. Now I'm sure in classical mechanics and everything, you know the formula of escape velocity and definition of escape velocity, but I'll anyway give you a brief outline of that also. Once you are equating those two conditions, then also they have mentioned the mass of nitrogen atom, that is to take Earth's gravitational acceleration of g is mentioned, and the radius of the Earth, which we denote as r subscript capital E, is also mentioned in kilometer. So here we will prefer to solve in SI units, so everything will be in SI. So like in this case you have to convert this kilometer to meter. Then for nitrogen atom this is in AMU units, but you have to convert it into kilogram in this case because we are trying to do in SI. And by then using the condition that you have to equate the two velocities, you will get the answer. So let us then try to solve it. Now again I will be choosing the white marker. So this is our question number 4. Now so it is saying that first of all it is nitrogen molecule. Let me write that down. Then the CRMS or the RMS velocity of the nitrogen molecule has a formula like root over of 3 kT by m, where T is the temperature in Kelvin, K is the Boltzmann constant, and m is the mass of a single molecule of nitrogen. Okay, so and what is the escape velocity in this case? Because that is the other velocity that you have to know and equate with this CRMS. So escape velocity is basically the velocity by which, if you get that velocity to a particle, then that velocity will just escape the Earth's gravitational field, and basically it will not be confined into Earth's atmosphere anymore. So this is the escape velocity. This is the well-known standard expression of escape velocity V subscript E is equal to just root over of 2g capital R, where R is basically the Earth's radius, because in this case we are calculating Earth's escape velocity, or some particles escape velocity on Earth basically. So because of this is the radius of Earth itself. If you take some other planet, then you have to use that planet's escape radius. Okay, so radius of Earth, g is the gravitational acceleration, that is a standard constant, and this is the formula. Okay, so once you have the formula, in the question it is mentioned that for nitrogen molecule these two are equal at a particular temperature T, which is unknown to you. You have to calculate. So your CRMS equal to VE for nitrogen molecule at temperature T. So just equate this root over of 3 kT by m equal to root over of 2g Re. Right, so both sides are root under root, so you just cancel out the square root by squaring both sides. This is 2g Re. Then your T is just 2g Re into m by 3k. So you see that we have directly obtained the expression of temperature in this case. Now you have to just put down the values of the different terms. So this G value and Re value is mentioned to you in the problem itself. Now this m value is also mentioned, but as I said that you have to be very careful while writing down the m, because sometimes just because of a mistake in the idea itself, it can give you a different value. So they have mentioned that this m for a nitrogen molecule, for a single molecule, is given as, I think they have given 23 point, sorry, let us check one second what terminology they have used, because this can be very tricky sometimes. So they have mentioned that this is nitrogen atom's mass. That means mass of a single nitrogen atom is 23.24 AMU. So in nitrogen molecule, I said that this is a diatomic molecule. So this has two nitrogen atoms. So basically it will be 23.24 into 2 AMU. Why 2 into 2? Because this is for a single nitrogen atom, and into 2 because nitrogen molecule is diatomic. It has 2 atoms. So that is why you have to remember to multiply it by 2. Also there is a catch. Okay, as I described to you earlier, that whenever you are given this unit, atomic mass unit, to convert into gram or kilogram, you have to multiply by that inverted Avogadro's number. That means basically 1.66 into 10 to the power minus that 27 kg factor. But in this case, there is a slight problem in the, I think this problem is in the question itself. I think the question should be framed differently. They have mentioned 23.24 AMU. Here basically what they have done is that they have basically, you know that for nitrogen, for a single atom, this is standardly known, you can check Google, that this is 14 AMU for a single nitrogen atom. Okay, so basically if you now try to write it down in terms of gram or kilogram, what you need to do is that 14 into 1.66 into 10 to the power of minus 27 kg, right? What they have done is that they have coupled these two terms together. If you multiply this 14 into 1.66, you will be getting exactly 23.24. So they have given the term like that, which I had figured out after solving, and I was not getting the answer, so I looked out that what is the problem. So then I found out that this is the thing that is given, but generally this should not be written like this. So anyway, we'll be just considering that this is the value that they have tried to mention to us. So because nitrogen is a standard element, its atomic mass cannot change, so that way you already know that nitrogen atom has 14 AMU mass, so from which you can directly calculate and neglect this thing if you have confusion in this part. But basically I will be doing the same, that this is for a single atom 14 AMU, that means for two atoms in a single molecule it is 14 into 2 AMU, which is 28 AMU. Now for a single molecule of nitrogen, when you convert it into gram or kilogram unit, it is just 28 into 1.66 into 10 to the power of minus 27 kg. Or this is the same as, if you see, this will be the same as 2 into 23.24 into 10 to the power of minus 27 kg. Because this 28 is 2 into 14, and 14 and 1.6 is multiplied to be 23.24. So once you have the mass expression, then you just use the formula we have earlier. Always use the same unit, so you will be using all SI unit. So this is 2, SI G value is 9.8 meter per second squared. Then the value of Earth's radius is 6,400 kilometers, so you convert it into meter, into 10 cube. Into then mass is, I already wrote it down, 28 into 1.66 into 10 to the power of minus 27, this one. Then by 3 into K, Boltzmann unit in SI 1.38 10 to the power of minus 23. If you calculate this, use your calculator, this will be 1.4 into 10 to the power of 5 Kelvin. So just check the options. One of the options will be this. So let us go back. Yeah, so option number B is, in this case, is correct. Option number B. Okay, so this question is also done. Then let us move on to question number 5, which says that find the RMS speed of molecules of a gas with density of 0.3 gram per liter of a pressure of 300 millimeter of mercury. Now this question is a little bit different from the earlier ones, but again the idea is same, that you have to know what you have to solve and then what are the clues and get a connection or connecting formula between them. So you have to know the RMS speed of a gas. So CRMS is the thing you are looking for. Density is given. Density is mass by volume, which we denote as rho. Rho is 0.3 gram per liter. If you prefer to convert it into from CGS to SI, so basically 0.3 into 10 to the power of minus 3 kilogram divided by liter is the volume. In this case, liter means decimeter cube, right? Decimeter cube is practically known as liter. So if you have to convert it into SI, so then you have to convert it into as meter cube. So decimeter cube to meter cube is basically 10 to the power minus 3 again. So this cancels out and you are left with only 0.3 kg per meter cube. So basically gram per liter equivalently gives you the same value in kg per meter cube. But this is in SI. At least we have checked that. And the pressure is mentioned. So the pressure P is 300 mm. Now this is a standard unit of pressure that you write it down in terms of the height of the mercury. So in this case the height is 300 mm and we write it down as 300 mmHg. This is a very standard expression. So 300 mmHg is our pressure. Okay, but you have to convert into SI units as I said. So again there is a direct conversion. You can check internet that 1 millimeter Hg of pressure is equivalent to, in Pascal you know that SI unit of pressure is Pascal. So this is 133.3 Pascal. Okay, so from that you can directly get what is the 300 mmHg is equivalent to how much Pascal in SI. So this is just multiplied by 300 and you get the SI unit of pressure. Now the connecting formula is you have to know. So question number 5. So you know CRMS equal to earlier known as root over of 3 kT by A. Now you know there is also another alternative expression that it is root over of 3P by rho. Okay, where P is the pressure and rho is the density. This is also an alternative expression of CRMS. And how to get that? I will also show you that there is an expression called Clapeyron's equation where P is written as NKT. Okay, so this is the Clapeyron's. Now I can skip this part also, but I am writing this extra information down because sometimes you have to use this equation in some other formula just to get your answer out of that relation. So this is pressure. N is the number density of molecules. That means number of gas molecules per unit volumes. So it is capital N by V. V is the volume and N is the number of molecules. K is the Boltzmann constant and T is the absolute temperature. So if that is the case, and also you know rho is the mass density, which is small m by V, mass by volume. Okay, so then this root over 3 kT by m is basically you convert it into P equal to N kT, so kT equal to P by N. Okay, and basically it is root over of 3P by Mn. Now you will see that m times n is nothing but rho. Why? Why m times n is rho? Because m times n is m times capital N by V. So number of molecules is capital N. Each molecule has mass small m. So the total mass is m times capital N by V, which is nothing but your rho. So in this case there is a terminology issue. Let us call it, let's say, capital M. So remember capital M is here not the molar mass that we usually denote, but capital M is basically the total mass for all the molecules present in the gas. So in this case rho is capital M by V, which is equal to also small m times N. So this is how you get this. Now once you know this, you just directly use the known values to you and just use it in proper unit. Okay, so as I said, 300 mmHg is just 300 times 133.3 Pascal in SI unit, and rho is just it was 0.3 gram per meter cube, kg per meter cube, which is also in SI. So if you calculate this, you will get 632.3 meter per second. So this is our answer. Now check which one is correct. So this is option number D. So our correct option is D for this case. Alright. So we have 6, 7, 8, 9, 10. 5 more questions left. Let us see how much time is left, whether I can solve extra problems or not. Okay, we still have an hour. So question number 6. It is again based on Maxwell's velocity distribution law, and it is said that the Maxwell's distribution for velocities of molecules is given by NCDC equals to this 2 pi n into this whole expression is given. Okay, and you have to calculate the value of 1 by c. Now Another problem here is that they have like there is a problem in the question. They have mentioned 2 pi, it should be 4 pi. You know, in the earlier problem we had used that expression. This is a correction, please note, this is 4 pi. Okay, and this NCDC is nothing but the DNC I was writing earlier. So the number of molecules in the velocity interval C to C plus DC. Now this distribution standard form is given and you have been asked to calculate the average value of 1 by C. Okay, so 1 by C, this expression means here that you have to calculate the average of 1 by C. So this is basically similar to any probability distribution function. If you have been given, how do you calculate the average? So basically, if this is your DNC, which is the probability distribution of gas molecules by Maxwell in this case, then how do you do that? So you just take the quantity that you have to take the average over. In this case, it is 1 by C. Then you multiply it by the probability for that particular term, which is a probability distribution term in this case, which is DNC. Then you integrate it over the total range of that distribution, which is in this case C equal to 0 to C equal to infinity, which is a standardly known distribution limit of Maxwell gas molecules. And you have to then ultimately divide it by the total number of molecules so that it is averaged out. So that is how you get it, right? Like like very similarly that you, let's say you have been given red colored balls, 5 pieces, and 10 balls of green color, and let's say 3 of black. Then how do you, like, sorry, I have to mention not like this is not a proper example, I think. Like I think you get it. I do not have to like explain the probability distribution to you right now, but just a similar way, just each quantity you take and the corresponding number you multiply, then you average you take integrate it out over the whole range, and finally you have to average it out by dividing by the total number. So this is the idea. So now just the only thing you have to derive over here is that you have to get the integration right, because there is such a huge term that is written in the form, right? So you have to get the integration right and you will get the answer. So let us do step by step. Now be very careful and follow each step, each line carefully. If you have any doubt on a step, just right away ask me. Okay, so you do not have to even raise your hand. You can just like cut me in between and interrupt me and ask. Okay, I don't mind. So now let us begin. You have to get the average of 1 by C. As I told you, the main starting formula will be 1 by n, then C equal to from 0 to infinity integration of 1 by C dnc. Okay, dnc is coming from Maxwell's distribution, so let us write that down. 1 by n is constant, so it is outside the integration. 0 to infinity 1 by C. dnc in this case is basically nothing but the nc times dc in the problem. So that value is 4 pi n c squared m by 2 pi kt to the power 3 by 2 e to the power of minus m c squared by 2 kt dc. Okay. Now to make it simpler, we just take out the constant terms outside so that only the terms relevant for the integration are inside. So like n and n constant, they cancels out each other, and the remaining constant terms that comes outside the integral is 4 pi into this term. This term has nowhere c because this integral is over c, so you just want to keep the terms related to c inside the integral, and all other terms are considered as constant and they come outside the integral, like this term m by 2 pi kt to the power of 3 by 2, right? So then 0 to infinity, then c squared, I think, oh, there was also 1 by c, so this 1 by c and c squared cancelling out, so only 1 c, then e to the power of minus mc squared by 2 kt to dc. So this is the all everything that we need for the integral. So let us for now forget about this part, only deal with this part, integrate this out first, and then we'll get the final answer just by multiplying this constant. So the variable in this integral is c. Now how to do this integral? First we need to redefine the terms, so that this exponential, this huge term, we redefine as mc squared by 2kt, we redefine as x. Okay, so then m by 2kt into 2c dc equals dx. Then this 2 and 2 cancels out. Then c times dc is just kt by m dx. Okay, so you see that our job is very much simplified, because now this is e to the power of minus mc squared by 2kt into c dc. So you take the c with this dc, so that now you can directly use this value here. So you just substitute the terms in term of c to x to simplify them, so that they look simpler and it is much easier to solve. Okay, so now because x and c are related, so if c is going from 0 to infinity, then x is also going from 0 to infinity, because they are related like that only, they are defined like that. So the x limit, whenever you change the integral variable from c to x, the limit remains the same in this case, because this is defined like this. Okay, let me just switch on the charging. I think I have to charge this phone. 1 second. So continue. Yeah, so we redefine the variables. Now this mc square by kt is x, so e to the power of minus x, and c dc is just kt by m dx. Now just see how much this total term has been simplified now for us to solve. This kt by m is constant, so it comes outside the integral. E to the power of minus x dx 0 to infinity. This is a very simple integral. You do this all the time. So this is kt by m e to the power minus x by minus 1 0 to infinity. So this is just kt by m e to the power 0 minus e to the power of minus infinity. Now you know e to the power minus infinity goes to 0, and e to the power 0 is 1. So this is just kt by m. Now you have already got the solution to the integral part. This is solved, and you have to just multiply it with the initial constant part to get the final answer. So the final answer will be 4 pi m by 2 pi kt to the power 3 by 2 into, what was that? It was kt by m, I think, into kt by m. So let me separate it. Okay, so this is I've done this right now. Yeah, it was kt by m probably, and then just 4 pi. Just simply let us simplify the terms again. So this is m to the power 3 by 2 means m root over m. This is 2 pi. Then kt into root over of kt, because 3 by 2 this thing is there, and also 2 pi will be like 2 pi into root over 2 pi. Then again kt by m. So this kt and kt cancels out, this m and m cancels out, and this 2 pi and 4 pi cancels out to be 2. Okay, so this 2 and this root 2 will be root 2 in the up. So this is root over 2m by root over of pi kt, which is in simpler terms, so this is just 2m by pi kt to the power of half. I think this was given in option number B in this case. So let us go back. Option number B, yeah. So this is the answer we have obtained. So it has come right. Okay, B. So you got the idea that whenever, if let's say instead of this 1 by c any other term is present and given to you in your problem, then the main idea is same. Just instead of 1 by c you have to use that and do the integral in the same way. Just divide it into term by term, break it down, try to simplify the terms of the integral by substituting and change of variables, and finally recombine every term that is there in the whole expression, and you will get to the final. Just you have to patiently do step by step, and so that you do not miss out a single term. Okay, so I think in your assignment there is a problem similar to this where you have to calculate c cube, I think, or I don't remember. It can be similar to that. Now question number 7, saying that if the density of a gas is 1.78 gram per liter at NTP, so NTP means natural temperature and pressure. So whenever NTP is mentioned, you have to understand that if even if there is no explicit mention of the typical pressure and temperature on that in that situation, but it means that natural temperature and pressure means it will be equal to 300 Kelvin, and natural pressure, you know that this is just 70, I think it was 76, I think 76 mmHg. Let me just check. How much question? 1 point, or you can also say this is, instead of in mmHg units you can directly use 1 atmosphere also, because 1 atm means 1 atmospheric pressure, and there is a direct relation to this in Pascal. This is just 1.013 into 10 to the power of 5 Pascal. So basically normal atmospheric pressure is the pressure in NTP, and the density is given, that means rho is given, and molecular weight is given as 4. Molecular weight, remember, so 4, that is nothing, no gram, kilogram, nothing mentioned, that means this is 4 AMU unit or atomic mass unit. Okay, and it is said that calculate the kinetic energy of the gas per mole. Okay, kinetic energy at NTP per mole. So what is the thing that you have to use here? First of all, kinetic energy is given in the general expression of half mv square, right? So where half into mass m times velocity square. This is the basic kinetic energy idea. Now if you have been asked per mole, so that means the mass you have to use there will be mass per mole. Okay, and the velocity you have to use here is obviously the RMS velocity, because you know that the gas will have many more particles, many more molecules which will have a total distribution of velocity. So whenever there is a distribution you have to use the RMS velocity. So that will be the velocity effectively in this case. So first you have to calculate what is the RMS velocity, and you have to know the mass per mole in this case, and combine everything to get your half mv square kinetic energy expression. So that is the idea. Now let us write down the terms together. This is question number 7. Now there is no specific system that is mentioned, just rho, the density, mass density is given as 1.78 gram per liter. Now we just in the previous problem we understood that gram per liter is basically equivalent to kg per meter cube, because it does not change the initial value. So 1.78 kg per meter cube, this is in SI unit you have converted the density, and weight, molecule weight was given as 4 atomic mass unit, that means per molecule. So now again there is a trick, that if 4 AMU is given, that means this 4 is nothing but the value of the molar mass, right? Because in case of nitrogen, let's say we write 28 AMU for N2. So what is 28? 28 gram is the mass for the 1 mole of that nitrogen. Similarly, whenever there is given in atomic mass unit, why do we for a single molecule, if you have to convert it into a single molecule's mass, because of the same reason we have to divide it by the Avogadro's number, because this by default means that for 1 mole of the system the mass will be in 4 gram. So it means that 4 gram is the weight for 1 mole, which is Avogadro number of molecules. Now in our case we don't have to convert anything because already they are asking us to calculate in per mole. So this weight is directly what will be using as the mass for 1 mole. So this is the system's 1 mole's equivalent mass or weight is 4 gram. Remember this is in gram, so if you have to go in SI, so this will have to be in kilogram, 4 into 10 to the power minus 3 kg. Now NTP is there. Okay, that means temperature and pressure is normal temperature and pressure. So now kinetic energy Ke of the system per mole, that means of 1 mole of the system, is equal to half mv square, half into m to v square, where this m is capital M, that means mass of 1 mole or molar mass, whatever you prefer to say, and this v is the CRMS or the RMS velocity. Now you have to know what is CRMS. CRMS, you know that this is either 3 kT by m or the alternative formula is root over of 3p by rho. Now given in this problem, you have to understand that the formula you will be needing to use is 3p by rho, because rho is given to you and p is also mentioned in the NTP value, right? So we will be using this clue only. So root over 3 into P is basically your it was what natural temperature and pressure, right? So 1 atmosphere is nothing but 1.013 into 10 to the power of 5 Pascal or SI unit, divided by rho is just 1.78 kg per meter cube, again SI unit. So this will be your 413.19 meter per second RMS velocity. Then use that expression CRMS squared. So this is half times the mass is molar mass 4 kg, that means 10 to the power of minus 3 into RMS velocity is 413.19 whole square. So this will be like 341.46 joule, or this will be 3.41 into 10 squared joule. So this will be your option number C. So go back and check. Yeah, so this is option number C. Okay, right. Now question number 8 is that calculate the temperature of an ideal gas at which its RMS velocity will be 1/3 of its value at temperature 900 Kelvin. Now again a similar type of a problem, we had already solved similar thing before. We have just to use the direct expression of RMS velocity and how does it connect to T, because everything else will be constant, only the temperature dependence will be taken into consideration, and then you have to just take the proportionality relation and give the ratio of them, so that you use this condition that RMS velocity will be 1/3 of its value. So let's say you have to calculate what is T1 of an ideal gas. Now at T1 the RMS velocity is C1. At T2 is 900 Kelvin, let's say, the RMS velocity is C2. Now the condition given to you is that this C1 will be 1/3 of C2. So C1 is 1/3 of C2. So just directly use this again. So T2 is, I think, 900 Kelvin. In this case the velocity is RMS velocity is C2 and T1 is unknown, but at this temperature the RMS velocity is C1, and the relation is that C1 equal to C2 by 3. So basically C1 by C2 equal to 1 by 3, and you know that RMS velocity is proportional to root over of T when everything else is constant. So your C1 by C2 will be like root over of T1 by T2. So basically your root over of T1 by T2 equal to 1 by 3, or T1 by T2 will be 1 by 9, So T1 will be like T2 by 9, which is 900 by 9 equal to 100. So it is simple. Just 100 Kelvin is the answer. So this is our answer, option number B. So now you get the idea, right? So what kind of problems are coming and how to solve them. So this is 100 Kelvin, option B. Now question number 9. Calculate the ratio of specific heat gamma for a mixture of 1 mole of an rigid ideal diatomic gas and 1 mole of an rigid ideal linear triatomic gas. Now here comes the portion where the degree of freedom and how that relate with the specific heat ratio gamma of and how to actually get the mixture of ideal gas cases specific heat. So these ideas will be coming into the picture. Okay, so let us try to solve it. Now instead of okay, just one second. Yeah. Um. Okay. Okay. So let us continue. Okay. So as I was saying that there is a mixture of two ideal gases. Okay. So ideal gas number 1, let's say it has the number of molecules as N1. Its degree of freedom is F1. So this is the first kind of a gas which is like rigid diatomic gas they have given. Let's say this is gas 1 we denote. And the second one, ideal gas number 2 in the mixture. Let's say the number of molecules total present in here is N2 and the degree of freedom in this case is F2. This is a linear triatomic gas. Not just triatomic, because triatomic gases can have two different categories depending on how they are arranged. So if they are linear or they are triangular shaped arranged, depending on that the degree of freedom will change. So basically we denote linear in this case, right? Okay. So once you have that, you have to use the idea of equipartition of energy. Equipartition of energy. It tells you that the energy is uniformly distributed for all the molecules in a gas and for throughout its all degree of freedom when it is at a particular temperature under thermal equilibrium. So in this case it is important to mention the temperature. So T is the thermal equilibrium. When the mixture is at thermal equilibrium, its temperature is T. Of the mixture, right? Now if that is the case, then you know that the mean kinetic energy of a system per molecule and per degree of freedom, or in short DOF, of that system at a fixed temperature T in thermal equilibrium is equal to just half kT, where K is the Boltzmann constant and T is the temperature. So this is the equipartition theorem. Now if there are N1 molecules present in the gas and there is F1 degree of freedom for that gas, then for all of them, what is the mean kinetic energy in total? Then it is just multiplied by N1 and F1. So half kT into N1 into F1. So this is for gas number 1. And what is this? This mean kinetic energy is basically we denote as the, we also assume that there is no potential energy or interaction acting into this in this picture. So the total internal energy is only coming from the kinetic energy. So then total internal energy of gas 1, which is diatomic, is equal to U1 is just half kT N1 F1. Similarly, Total internal energy of gas 2 will be like, again by equipartition, it is U2 equal to half kT, because this is a different gas, its N2 is different, in total number of molecules is different, and degree of freedom is also different. So then the total mixture of gas 1 and gas 2, mixtures, total internal energy U is just U1 plus U2. So this is half kT, this is in common, then N1 F1 plus N2 F2, right? So if you now have to calculate the specific heat at constant volume, you know that that is just du dt at V constant. You have to take the derivative of U at with respect to temperature. So then it is just half this one's derivative. So half K, just T takes off by the derivative. So this is half K N1 F1 plus into F2. And then what is Cp then? So you know that there is a relation between Cp and Cv. So specific heat at constant volume and specific heat at constant pressure. So this is just total number of molecules, which is in this case N1 plus N2 in the mixture, into R. R is the universal gas constant. So for 1 mole of gas, the relation is simpler. Cp minus Cv is just R. But this is for 1 mole. In this case, you have I think, okay, sorry, there's a let me check the problem once what is given. Yeah, so I made a mistake in the definition of the case in this case. So this is in this case mole is given. So let us consider that this N1 and N2, obviously this is the number of molecules, so I have to write an extra term also if we try to write it down by moles, because that will be easier for us, because in the question it is mentioned moles as an as a terminology. So for N1 moles, let's say it has N1 into Na number of molecules, so we just have to multiply by an extra term which is just the Avogadro constant. Okay, so this is just then N1 F1 times Na also. Similarly, if for gas 2 there is N2 number of moles, okay, this is the number of moles and not molecules. So then there also there is another Na terms that is coming. This is just Na that will be multiplied here. Okay, other things will remain just the same. So it is a constant. Na comes outside. This is K times Na, N1 F1 plus N2 F2. Now, because for 1 mole this is just R, so for a mixture this has N1 mole of gas 1 and N2 mole of gas 2. So the total number of moles of the mixture is simply N1 plus N2. And you also know that your R is nothing but Boltzmann constant times Na. So here you can also write it like R by 2, because this K into Na is R. N1 F1 plus N2 F2. Now, so Cp equal to Cv plus N1 plus N2 R. Cv is known, R by 2 N1 F1 plus N2 F2. So just R by 2 now simplify this out. So this is just R by 2. Then if you take N1 as common, then N1 F1 plus this is R, but here you have taken common 2 also, so this is 2R, right? So this is just F1 plus 2, plus then take N2 as common here with F2, again here this will be a 2. So this is just R by 2, this whole thing. I will not write it down again. So then gamma is specific heat ratio, which is the ratio of Cp by Cv. So if this is your Cp and this was your Cv. So this r by 2 cancels out, the other terms are remaining. So let us write that down. So this is n1 times 2 plus f1 plus n2 times 2 plus f2 divided by n1 f1 plus n2 f2. Now in the question it is mentioned that gas 1 is of 1 mole, that is n1 1 mole, and n2 is also 1 because that is also 1 mole. So n1 equal to n2 equal to 1. Now you also have to know what is f1 and f2. So f1 is the gas 1's degree of freedom, which is a diatomic gas. So you know that the degree of freedom formula is 3n minus m, where n is the number of atoms here, m is the number of constants present in the system. So for a diatomic case, this is just two atoms that are connected to each other by some bond. Okay, this is diatomic. So this is their constant. There is a single constant that restricts itself to move in any particular direction. Otherwise, there is no other constant. So this is m equal to 1 constant because of this bond of diatomic, and there are two more atoms present. So n equal to 2. So this will be like, and 3 is because this everything is 3-dimensional generally. So this is 3 into 2 minus 1, which is 6 minus 1 equal to 5. So for a diatomic gas, the degree of freedom F1 is calculated to be 5. Similarly, what will be F2? F2 is for gas 2, which is a linear triatomic gaseous system. Now this terminology is important because how to structure the system will be based on that. So if it is triatomic, so there are 3 atoms. If this is linear, then it will be like this in a rod or in the same line. This is atom 1, atom 2 and atom 3, and there are in between 2 constants restricting them. So this is m equal to 2 and number of atoms is 3. So in this linear case, F equal to 3 into 3 minus 2, 9 minus 2 equal to 7. But why linear has to be mentioned? Because otherwise if it is not linear, then it can also form a shape like this, right? Again, this is triatomic, it has 3 atoms at 3 corners of the triangle, but here the number of restrictions are 3. There are 3 lines like that. So equal to m equal to 3, n equal to still 3, and then it is f equal to just 3 into 3 minus 3, which is 6. So depending on how is the structure, linear or non-linear, the degree of freedom changes. So in our problem, this is linear, so this is f2 is 7. Okay, right. So then just put it down in the formula. Gamma equal to, then n1 is capital 1, then 2 plus f1 is 2 plus 5, plus n2 is 1, then 2 plus f2 is 2 plus 7, divided by n1 f1 is 1 into 5, plus n2 f2 is 1 into 7. So simply the answer will be 16 by 12, which is just 4 by 3. So this is our gamma. This is your option number A. So we have calculated this gamma. Now one last question is left. After that there will be some time. We will be solving 2 or 3 extra questions outside this assignment, which will be helpful for you, just like I said. Then the last question is interesting because it says that this is a physics based question, not just mathematical like the earlier ones. So it is saying that consider the Maxwell speed distribution curve of an ideal gas at 3 different temperatures, T1, T2 and T3, such that T1 is greater than T2 and it is greater than T3. That means T1 is the highest temperature and T3 is the lowest temperature. Then at which temperature the curve will be having the maximum broadening. Okay, so we have to understand how the Maxwell speed distribution curves are drawn and what is the effect of temperature on that distribution, and based on that we will be answering this question. So let us go to a blank page because I need to draw the diagram and write something also. So this is question number 10. The heading would be effect of effect of temperature on Maxwell velocity distribution. Okay. Now, if you remember what was the distribution formula in our case, so just writing it down. dNc equal to what? Yeah. So dNc is equal to 4 pi m by 2 pi kt to the power of 3 by 2 e to the power of minus mc squared by 2 kt c squared dc. This was a distribution function formula, and this is the number of molecules having velocity between c to c plus dc. Now this c is basically a velocity which depends on temperature, of course. This is temperature dependent. So everything in this formula or this distribution is valid in a particular way at a particular temperature. Then at a different temperature the values might change, but the overall structure, means this distribution curves overall structure will remain the same, but there can be a shift depending on what? Basically depending on this condition, that your integration over dNc from c equal to 0 to infinity equal to 1. What does this mean? This basically means that your this is not 1, but this is dNc by this n will be 1, because c equal to from 0 to infinity dNc integral will be total capital N. That means if you take the number of molecules between c to c plus dc interval, this value, but you integrate all the intervals, like if you integrate all the total range from c equal to 0 to infinity, that means you are covering all molecules that are present in that gaseous system, right? So by default the integration result will give you n. That means the total number of molecules present in a, so let us define this dNc by n as some Fc. Fc in this case is the probability distribution function for the Maxwell's velocity distribution. So this is the probability distribution function of velocity of the gas molecules. This is a short form of probability. So you know, like any other probability distribution function, the total integral will always be 1. So in this case you integrate over c as a variable. So here again c's limit is from 0 to infinity, but this has to be satisfied and this is getting satisfied. But this means the conservation of the total number of molecules. The total number of molecules present in a gas remains constant. Even if we change the temperature, that can change the velocity of the molecules, that can change the distribution, how the molecules are distributed under different speeds, because the speed will be changing with temperature, but the total number of molecules present in the gas will not decrease or increase or anything by the temperature change. So it remains constant even if you change the temperature. This is the formula for that under probability distribution function.
Ma'am,
Yeah.
ma'am, is it applicable only to monoatomic gas molecules or to all other types?
What thing? This distribution?
Yeah. Yes, ma'am.
Uh, in principle, monoatomic gas is basically taken for convenience of this. I mean, because you can understand it better, you can directly have to choose that's just one atom in a single molecule. But so basically for convenience purpose, it is for monoatomic. But because this is a classical distribution formula, so this will be applicable for other cases as well. But of course this is
Okay.
I mean this is a stand even this is a simplification of the total thing, because this is all obviously in classical where the energies are considered in a continuous manner, but in real cases most of the times energy is quantized, right? So this is just a classical generalization of the whole thing. So but yeah, your question's answer is that it will be valid. But the derivation is most likely done, most of the cases done taking it as monoatomic, so that it does not cause much of a complexity in the derivation. Alright, so if this is the thing that is getting satisfied, then if you can draw the distribution curve, what it will be like. So this, if you remember, if you know the form, if you look at the form, this has a Gaussian term like this here, e to the power minus x squared, some bx squared sort of thing. But also there is multiplication by c squared, so this is not completely Gaussian, it's also because this is multiplied by a c squared terms, quadratic term ahead. So the form will be something like, you can check from the book or internet, because sometimes when I am drawing it, it may not be accurate. But this is a rough form. This is fc and this is your c in the x-axis, velocity in the x-axis, probability distribution function fc in the y-axis. This is the curve that you get from c squared times some e to the power of minus bc squared sort of a Gaussian term. Okay. This will be asymptotically falling down. This we don't know, so this is just extend. Now this is a general case, but how it will change with different temperature. First of all, you know probably that whenever you are given such a thing, what is the area under this curve? So if you just dash, if I just mark this region by this dashed lines. Okay, so this area under the curve is simply the integration of fc dc, c equal to from 0 to infinity. So basically in other terms you can say that the total area under the curve actually is giving you the the total number of molecules present, sort of like that, because fc is just dnc by n, right? So then if you take fc dc, the n term comes out because this is constant, otherwise this is dnc dc. So this will give you n, the total number of molecules. So this is ultimately 1. So basically the area under the curve is mathematical equivalent of taking the total number of molecules which is present in the gaseous system. So this area has to be fixed. The only thing that can change is the distribution of the velocities at different temperature. How? Because let's say the most probable velocity, we denote it by cm. Cm is the most probable velocity. That means this is the velocity at which you can find the maximum number of molecules in that system. Or in other terms, this is the velocity where we will see a peak in the velocity distribution curve, this peak. So this is coming at a velocity which we denote as cm, the most probable velocity, because maximum number of molecules in the gas are confined into that velocity's order. Okay, and then you also know from the other definition of the other velocity, which is the average velocity, c average. This comes right after that, and the c rms is the rms velocity, which can be placed like this. So this formula is the derivation you know from the lectures already. So it has different expressions as well, and every expression has a t dependence. Means c bar is the average velocity is root over of 8 kt by pi m. This has a t dependence. Then CRMS you already know, this is root over of 3 kt by m, also t dependent. And C most probable, this is also derived, this can be derived, this is root over 2 kt by m, this is also t dependent. That means everything is dependent on t. Or in simple terms you can say that if the temperature is increasing, the thermal energy to the molecules is increasing. So it will be more likely that at higher temperature the molecules will tend to have a higher velocity. But basically because it is a distribution, so the velocities can be any value from 0 to infinity in total. But what will matter is that how much molecules are crowding around a particular velocity. Let's say if you have, let's say 3 different temperatures are T1, T2 and T3. So we go by the question, like there they have assigned T1 to be the highest temperature. So let's say our T1 is 300 Kelvin for example. T2 is 200, is a in between temperature, and T3 is the lowest one, which is 100 Kelvin. And you have three boxes of molecules which are exactly identical, but they are at three different temperatures, T1, T2 and T3. So these molecules of gas are present inside, and they are randomly moving around inside the container. Okay. So now very naturally, okay, so they have this random motion by kinetic theory. So very naturally, the gas molecules which are sitting at the highest temperature T1 will have much more excited, much more thermal energy compared to the other ones. So more thermally excited. So their most probable velocity, which is dependent on temperature proportionally, will be higher, or will be the highest among the three. If you have to define Cm1 for T1, then this box 2 has Cm2 and this say Cm3, the most probable velocity for the three cases, then we'll find that Cm1 is the largest one, then Cm2, and the lowest one is Cm3. Because the physical explanation is that the lower you go to the temperature, then there will be tendency that not much of the gas molecules will have a velocity in the higher range. This basically they will try to confine in the lower range mostly. So what will be the graph looking like for the three cases? So the case 1 where the temperature is T1, there it will be like this kind of a thing. Why? Because mostly here the velocities are confined in a lower range. That is why the peak is coming much earlier. And also another way you can guess it, which is the Cm1, because it is sorry, I wrote down the wrong thing. This is for T3, okay, this is for T3. This is for the lowest temperature, not the highest. The logic is that because the temperature is lowest, so the tendency of the gas molecules will be to be confined or crowded mostly around the lower velocity part. So that is why the peak is coming at a much lower velocity, and the most probable velocity in this case Cm3 is also at a lower side. That is why you see the peak much earlier, and then it is asymptotically decreasing. Okay, but this is at T3. But what happens at T1 or T2? First of all, let us see what happens at T1, which is the highest temperature. So at T1, the maximum temperature, so maximum velocity will be on the higher side. So your Cm, which is the most probable velocity that is proportionally dependent on T, will also be shifted towards the higher side, because now its value is has increased because of increased temperature. Now, so you see a peak here. Sorry, I have drawn wrongly, maybe. So then I'll just shift the Cm value, because Cm will be defined where the peak is, right? So let's say this is the peak. So this is your Cm1. Why this happens? Because Cm1 is now much higher end, so this comes to this part. But you can ask why the peak height has decreased. That is the idea that I talked about the conservation of the number of molecules. Because even if you are increasing the temperature, the number of molecules remaining the same. That means the area under the curve remains the same. So if you are increasing the width of the distribution, you are going towards much higher end. So then you have to decrease the height also, right? Because mathematically that is feasible. You have to keep the area constant. So if the area simplest expression is height times width, so if your width is increasing because your Cm is increasing with higher temperature, so then obviously your height should have to be decreased to keep the area constant. This is a mathematical idea, but physically you can think of it like that. As you are going towards higher temperature, all the molecules will have a distribution mostly towards a higher end of velocities. So the molecules are mostly distributed in higher velocity range all throughout. Earlier it used to be like most of the molecules are in a particular peak value. They are peaking at a single most probable velocity, but now they are distributed throughout this range. They are also distributed towards the higher range significantly, where this peak had to be fallen much earlier or much steeper, I will say, because not much molecules are present in the higher temperature, higher velocity range. But now that is not the case. So because of which the peak height has now decreased like this. So basically you can see the graph has widened. So you have already got the answer that if you increase the temperature, your distribution curve will be widened. So now if you plot three graphs at a single plot, this will be easier to understand how this behaves. This is FC versus C. The first one is at the lowest temperature, so it will have a huge peak value and it will decrease very sharply. This will not be wide enough. Yeah, so it is decreasing, and you identify the peak at CM1. CM3, sorry, this is at the lowest temperature, this is at T3, this is the lowest. Now you slightly increase the temperature, so let us then denote it by blue color. So then your CM will be slightly increased from before because you have increased the temperature, so this is CM2 at T2. Now the peak value is also be decreasing because, as I said, that now the velocities are also distributed towards the higher velocity side, so not only confined to this end. So you see that the peak height that has been now decreased. So because the total number of particles are conserved in the molecules are conserved, so that many number of molecules are now shifted from the this end. So number of molecules has not lost. You cannot think that okay, the height has decreased, that means that much number of molecules has gone somewhere. That is not the case. They are basically widening the graph, widening the curve. They are towards a higher velocity side. That is why the graph is looking like this right now, and this is as T2. T2 is the intermediate temperature which is greater than T3. Now the last one, the highest temperature is T1, and let's say we denote it by T by red. So here it is CM3. This is this, and CM3. At CM3 is the highest velocity will be there because it is proportionally dependent on T, root over T. And the peak height will be even decreasing from the earlier case, and it will be something like, it will be much more wider also. Here this will be the peak, and this is at T1. T1 is the highest, and it is the highest of all the three temperatures. Now again you see as you increasing the temperature, your width of the graph is increasing because the molecules are having a tendency of obtaining much greater value of RMS and most probable velocities, but the distribution peak height is decreasing because you have to keep the area under the curve constant because the number of molecules in total is not changing. Okay, so this is the idea that as temperature increases, the most probable velocity increases. That means the width of the graph, width of the distribution curve increases as more and more molecules now tend to have velocities in higher range. That means that will be covering x-axis much better, right, in a much wider sense. But peak height at the most probable value decreases because the total number of molecules has remained constant, that has not changed. Okay, so there are molecules which are present in many different higher velocity ranges, but at a particular velocity the number of molecules has now gone down. So this is the whole idea. So the answer will be, what is the answer? Yeah, so answer will be at which temperature the curve will be having the maximum broadening. So you see that with higher temperature it is broadened. So the one which is the highest, that is the T1 in this case, it will have the maximum broadening. Okay, so I think it is almost time. So we'll not discuss anymore. For this class we have covered 10 questions, and if you have still any doubt about any of these questions, you can ask me now. Or else if everything is clear, then I can stop today and we'll meet on next Sunday. So any questions, or we'll just finish? Okay. So I think there are no questions.
No, ma'am.
Yeah,
No, ma'am.
no questions. So you understood the problems?
Yes, ma'am.
Okay, very nice. Okay, then I think this will help you in this week's assignment. So let us meet next Sunday again with the next set of topics. Okay. Okay, all right. Bye.
Thank you, ma'am.